So thanks everyone for letting me come here and attend today. So as Melody mentioned, I am a brand new North Carolinian. I've lived in the Atlanta area for the last 25 years. And about 2 months ago, we up and moved to Wilmington. I recently inherited this territory from another gentleman from Tensar, Andrew Eisenhower. So a lot of you may know or be familiar with, but Andrew went on to a new position within Tensar, and I was fortunate enough to be able to fill his somewhat large shoes. So appreciate the opportunity to be here. And the title of my presentation is somewhat fancier, Geosynthetics for a Roadway Design Applications. Before I get too started, I know in ASCE meetings, there's always a mixed bag of different disciplines within civil engineering. Do we have any geotechs out in the room? A few geotechs? Okay, this will be very pertinent to you. Just general civils in the room, site development guys, general civils, this will pertain to you. Structural guys, structural engineers, a little bit pertain to you. And there's some stuff that I'm going to go over that y'all will definitely know more about than I do. And then I guess water resources, no water resource, good, we can make fun of them. Oh, yes, sorry. Sorry, guys. The only thing I've got for water resources is haul road. So there's always got to be a haul road built for those big pump stations and large water resources projects. As Melody mentioned, I am a graduate of the Mississippi State University, or as people in North Carolina would say, I am a victim of the Mississippi public school system. So you're going to have to put up with me today. Like I said, I have lived in the Atlanta area for the last 25 years. I've been with Tensar for about the past 7 years. I've been in this position with Tensar for the last year. Previously, prior to that, I was working on coastal protection projects and then large port projects all across the US. So Tensar is not just a pretty face. It's not just me. Obviously, some of you are familiar with Andrew. He was over this territory for, goodness, 12, 15 years. But it's not just Andrew either. So Tensar, we have more layers than an onion. I would be your first point of contact typically. Andrew still has his same cell phone number, so if you're going to call him, give him a call. Chris Vance is our area director, so he's over the entire Southeast. If you can't get me or Andrew, you can call Chris. David Fuquay is our area engineer, so when things get a little bit more technical or outside my zone of comfort, I can reach out to David. And I have all their email addresses here, but I'll be happy to share those with you after if there's any more contact information you want. But you might notice something a little bit different. There's not a lot of geotechnical or geosynthetics companies that have this amount of PEs working for them. And this is just Southeast and North Carolina. It's like this all across our company, all over the country. We're very, very engineering heavy. We look at ourselves more as a solutions provider than we do as a material provider. We really like to work with geotechnical engineers when they're developing their solutions, or civil engineers. We got a problem on site, can you guys come out and assist? We're not competition for geotechnical engineers. We're not taking your billable hours away. We're here to work with you. So with that being said, I know that ASCE typically gives out their own PDH, but I can make that even easier for you. So if you elect to, you can take out your smartphone, take a picture of this QR code, and you'll get an automatic email and endless spam for life. No, you will not get spammed. You have to physically check a box to enter into our marketing system. So if you don't wish to receive spam or updates on other presentations we may be giving, design workshops, things of that nature, certainly don't collect that box. And then you'll get a range of different courses to select for them. Just select Tensar 101. And I'll have this QR code up at the end of the presentation as well. So if you don't get it now, you can get it later. All right, so I love this slide. We've all had that call. I don't care what your discipline of civil engineering is. We've all had that panicked call from the contractor, where on the left, he's either sunk an excavator and he doesn't have any money. The owner doesn't have any of their money in the budget to deal with this. Or on the right, you got pumping soils. Just had a call this morning about a site with pumping soils. And it was self-inflicted wound. The owner tried to save money, and well, they saved money, but it's going to end up costing them twice as much. So how do we deal with that? So what I'm here today is, I don't have a golden ticket. I don't have a magic wand. I don't have pixie dust. I don't want the takeaway to be that Tensar says they're the one-size-fits-all solution for every problem you may have. We're another tool for your tool bag. If you get this call, you've all got your own bag of tricks. We can over-X and replace. We can do this. We can do that. I just want Tensar or geogrid to be another tool. It's like, hey, here's another option that may help us out of this. So that's the main takeaway I want you to take out of this today is Tensar can be there to help offer a solution for when we run into issues like this. There's a quick agenda, but you'll see that as we go along. So who is Tensar? As of last year, we are now considered a division of CMC. Has anybody in here heard of CMC? I'm always curious to see. One, GeoPeer, obviously. And then, so CMC is a Fortune 500 company. They own the market share for rebar. So chances are, if you've ever worked on a project and seen a piece of rebar on that project, it came from one of CMC's plants. So we're now a steel company. We're a plastics company that's owned by a steels company. And if you've ever driven down farmland and you've seen a green T-post, green fence post with a white top on it, that came out of a CMC plant. That's their little trademark, is the green T-post with a white top. So what does that mean to us? It means now we have a large company that's no longer a capital investment firm, but an actual manufacturer that shares their expertise with us, that shares their resources with us. And so far, knock on wood, it's been a good marriage. We've taken a lot of benefits out of it, and I'm kind of anxious to see what happens in the future. Tensar, we're a very innovative company. So we invented geogrid back in the 1980s. We've invented every notable improvement on geogrid since then. We've come out with different sizes, shapes. We're constantly doing research, and we'll talk more about that in the presentation. And we've produced almost 1.5 billion square yards of material so far. We own 2 plants now in the US. We own 3 others worldwide, although one of them's in Russia, so I'm not really sure how that all plays out. But anyway, we're a worldwide manufacturer. We have large presence in Europe, in Africa, and in Asia. So not only do we have people in the field that are working on a geographic basis, we also have people that are working on a market-specific basis. So while you're in North Carolina, you might make me a first contact. If you're working on, say, North Carolina, but if you're working on a petrochem project, we have guys that just specifically work in the petrochem marketplace. We have market managers that work in the rail marketplace. So if there's large rail projects, we have people that are in the rail industry that work specifically with that industry. Pavement maintenance or interlayers, public roads. So we have a lot of different markets that we focus on internally within Tensar. And so I have those resources available to me to, if you're running across this project, hey man, I know we've got this rail project, I don't have a lot of experience, can you help? Well, I would go utilize or leverage one of those guys within our office. And not only that, we have key account representatives that work with key accounts like the Kiewits and Ames, the large contractors of the world, the guys that specifically deal with them. So if you've ever dealt with Kiewit on a project, you know they're an extremely large company, but they're extremely fractured. The left hand has no idea what the right hand is doing. And somehow we've managed to, over the years, break through that and have learned to develop a really good working relationship with Kiewit, along with a lot of other large national contractors as well. So that's Tensar in a nutshell. All right, let's dive into it. Types of geosynthetics. So this is where I said, you know, I don't have a magic wand that gives you a one-size-fits-all solution. There are a ton of different geosynthetics that are manufactured for the construction marketplace. And all of these geosynthetics have a niche where they work really, really well. And then they have other applications where they work kind of well. So there's not a, like I said, you're gonna hear me say this a lot of times, there's not a one size fits all. Geotextiles work really well, certain applications. Geogrids work really well. Geonets on down the list. They all have their sweet spot. These are the main geosynthetic functions that you'll see: stabilization, which is dealing with soft soils or soft subgrades; reinforcement, which is basically what I call walls and slopes or grade separation; separation and filtration, which to me are very much the same thing; drainage layers. So we'll all see geosynthetic drainage layers that take the place of like 57 stone or clean graded aggregates that perform the function of getting that subgrade water out of your design area and then containment. So like geosynthetic liners. Where Tensar really plays with geogrid is in the stabilization and the reinforcement market. Now we do have fits in the separation and filtration area, but I wouldn't say you come running to Tensar as like, hey, I need to separate these two layers of soils. Yeah, maybe we can, but we're probably not the best fit there. Where we really focus our time on is stabilization and reinforcement. So stabilization, once again, dealing with soft soils, construction platforms, foundations, things of that nature. And reinforcement would be walls and slopes. Reinforced walls, reinforced slopes. So what are geogrids? All right, geogrids provide these different functions. Like I said, the main one that I'm going to talk about today is stabilization. And I brought in samples of different types of geogrids. So, you know, I said Tensar invented geogrids back in the 1980s, and this was the invention, the biaxial geogrid. We still sell a ton of this material. It is not our best seller, but it is up there. So we still sell this every day. Contractors use it every day. It still works well. Back in the late 90s, early 2000s, this was the next iteration. I told you, Tensar loves to research. We love to innovate. So this was the first big innovation that came out of Tensar was triaxial geogrid. So we have good, we have better, and we'll talk about that in the presentation. Then a couple of years ago, we came out with what right now for the marketplace is the best. This is Interact geogrid. And I'll pass these around in just a few minutes so you'll be able to see it. That's what an innovative company does. Like, hey, we take a good idea and we keep iterating and improving on it to make the product better, more financially feasible for the marketplace. And all of these geogrids here are used in that stabilization application. And then for reinforcement, we have the uniaxial geogrid. It's a really high tensile strength geogrid that's used to stabilize slopes. So as you might imagine, you do need that tensile strength in an MSE structure to stabilize it and reinforce it. And that's where uniaxial geogrids come into play. So here's a picture. We have a stabilized slope, and here we have a wall system. And maybe the geotechs can answer this one if they know, but there's a certain difference where a slope becomes a wall and where a wall becomes a slope. I think it's something like 70 degrees. Seems like splitting hairs to me. All of that is reinforced earth. That's all I know. It's reinforced earth. I know just enough about walls to be dangerous, but if you do have a wall question, you can come see me after. I'll be happy to address it or get you in touch with David Fuquay, who's our area engineer that can answer that as well. However, stabilization. This is our bread and butter. This is what we spend our day in, day out working on is stabilization projects, paved roads, unpaved roads, construction platforms, lay down yards, lots and lots of haul roads. You name it. If the softer the soil, the better the fit, the more phone calls we get. So how do geogrids actually work? We know that geogrids work. Most of you have probably seen them on a job site. Contractor will lay it out, dump some aggregate on top of it, and all of a sudden a soil that was moving and rutting becomes very stable. All right, that's pretty straightforward. But what are the actual mechanisms? As engineers, we want to dig a little bit deeper and understand how it actually works. Some really smart guys at the Army Corps of Engineers in Vicksburg, Mississippi, that run their soils lab there, commissioned a report to understand how geogrids work. And we know Mr. Jeb Tingle is a really smart guy because he attended the Mississippi State University with me at the same time. So Jeb, I think, now has his PhD possibly. So he's far outshined me in his career. But they published this report back in 2003, and they said there's three main mechanisms whereby geogrid performs. The first is the tension membrane effect. I have it labeled number 3, but we'll talk about it first. Tension membrane is simply like a trampoline. You step onto a trampoline, the trampoline has to go into tension to support you. That's how a geotextile typically would perform, is you roll a geotextile out over a soft soil, you step on it, or you roll aggregate out onto it, and then you have to rut it in. And so that geotextile has to go into tension before it provides the support that you're looking for. The problem with that is you're having to rut in that very soft subgrade, and you might make a bad situation even worse. The good thing is geotextiles do perform that separation function very, very well. So, there's a little bit of give and take there. As geogrid, we don't give the tension membrane effect much. We don't give that much credence when it comes to how a geogrid operates. There's a little bit of that there, and you can see that in the picture, but that's not mainly how it works. Second would be improved bearing capacity. just by the shape of the geogrid, we're distributing a load more evenly on the subgrade. So as we put loads down on this, it's spreading out that load just due strictly to geometry. So there's a little bit of that as well. The main mechanism and what you see there in that picture is aggregate confinement. Aggregate striking through the geogrid, interlocking, mechanically interlocking with the geogrid and preventing that rutting mechanism. And maybe we can see a better picture of that here. So the best way for me to envision that interlock, that mechanical interlock, is a rack with billiard balls. So if I lifted that rack up, those billiard balls would scatter all over the table. But because I have that rack there holding it in place, I can come and put a surcharge pressure on top of that billiard ball. And, 200, 500 pounds, I don't know how much it holds, but those billiard balls would remain stable because they're being laterally confined. They're being laterally restrained. Same exact way geogrid works. So if you'll notice, there is a vertical component to that where it's not just one layer of billiard balls thick, it's multiple layers. And that's the way it works with aggregate. We're laterally confining aggregate at the bottom layer, and that influence goes all the way up into the section. We've measured that up to about 16 to 17 inches into the section. So geogrid will have an influence on aggregate up to 16 to 17 inches higher. Is it the same as it is down low? No, but there is still an influence up there. So what we're trying to prevent, at the end of the day, our enemy is rutting. Whether that's on a construction platform or a paved road, we're trying to reduce rutting. And the way we do that, rutting is like a lateral mechanism. So what happens, you get the load from those wheels, the aggregate wants to rotate, and it wants to rotate out. And what the geogrid does is it restrains that aggregate, prevents that rotational motion, and reduces the rutting long term. So it's that simple. And it works. So here's kind of a better picture of it. You got the asphalt layer, we have that lateral shear flow, and then we have the aggregate base course that's being held in place because the geogrid is there holding it in place. This is another way to kind of envision that. This is a little dog and pony show. We'll do a trade show sometime. We call it the magic box of rocks. We build a box, we fill it with like GAB material, granular aggregate base, and then we pull the sides off of it. And as you might imagine, the whole thing slumps down. If you build that same box, you put the same aggregate in there, but you put 2 or 3 pieces of geogrid in it, and then you pull the sides on it, boom, it stays stable because of that lateral restraint mechanism. And that's really what that does a good job of envisioning. Now, we can't really design with this. I mean, this is just a trick that kind of helps you visualize how it's working, but that doesn't really help you as an engineer in your day-to-day designs. So I had mentioned, and I'll pass these around now, I had mentioned good, better, best. And how do we know that? And how does that come back to the lateral restraint mechanism? Here you see the biaxial geogrid. This is the highest tensile strength geogrid, short of a uniaxial geogrid. Of the 3 geogrids I have up here, this is the highest tensile strength. So if a contractor comes to you and says, hey guys, this is the strongest geogrid that I can get at my local supply house, that sounds great, let's use it. However, as you see here, it's probably the least effective. And it's all due to the height of the ribs. This is good. We sell a lot of this. It works. This just happens to work better. And this happens to work best. And I'll pass these around so you can kind of compare the rib heights on those mechanisms. Now, geometry plays into that. A few other things play into it with the chemical composition that we use. But by and large, the biggest benefit you're going to get is from that rib height, that rib profile. All right, so Tensar, innovation. We love to innovate, but we also love to prove our innovations. We love to test. So when we invented triaxial geogrid, we said, okay, let's do a proof of concept. So we have this small scale trafficker over in the UK at our plant there. I don't know why they don't move it to the US. So we would make these grids, would fly them over to the UK. They would put them in this small scale trafficker with like a 2% CBR clay as the subgrade. And then they would put an 8 to 10 inch aggregate layer on top of it, and then they would traffic it. So as you can see here, an unstabilized or no geogrid section, they were able to get 3,000 passes before the rut failure occurred. The BX geogrid, they got to 10,000 passes, but you can see the damage that was done to the subgrade. And then the triaxial geogrid, they got to 10,000 passes, and there was only a small there was only a small rut in the subgrade. Now this is after, these pictures down here at the bottom are after they pull the aggregate out of that small scale trafficker. And what's left is that subgrade layer, that soft clay subgrade layer. So we did the same thing with AASHTO geogrid. So we came up, I saw in a presentation, it was over 100 different shapes. So we have that kind of weird hexagonal thing going on with AASHTO now. Our guys at the plant developed about 100 different shapes of, hey, let's test all these different geometries and see which one works the best. And ultimately, the winner is the one that you have there. And when they did that, it's okay, let's put this in a small scale trafficker and compare it to unstabilized, no geogrid, to triax, which performed the best previously. Then we'll put the interax in there, the new geogrid. So you can see what happened to the subgrade. Very large rut there after 10,000 passes. Almost complete failure of that subgrade. Triaxial, a small rut, and the interax after 10,000 passes, almost no rut. You can see almost no transfer of those stresses to that subgrade from the trafficker. Very good job of distributing that load out widely, much wider. So this is just proof of concept. This just tells us, okay, we have a geogrid. We know it's going to work better. Now we have to go out and actually test it. So that brings in full-scale field testing. And as you might see here, we have a layer of mechanically stabilized aggregate, which has geogrid in it. And then we have a layer that isn't. It's very subtle, so you might want to keep an eye on this and tell where he leaves the unstabilized section, or where he gets to the unstabilized section. The only difference, same amount of aggregate, the only difference was one had geogrid, one did. So it's, like I said, it's not a golden wand, it's just another tool in your toolbox, but it's a pretty big tool. I love that video because that just kind of goes over it. So one thing to be aware of, and especially as those grids are making their way around the room, is I mentioned there's a lot of different geosynthetics that are used for stabilization applications. You got geotextiles, you have polyester geogrids, you have polypropylene geogrids, which are Tensar's products. Ron, what else are we using for underground stabilization? I mean, there's a lot of different solutions. However, they all have different mechanisms by which they work. So we're using lateral restraint mainly for geogrids. Geotextiles are mainly using that tension membrane effect. And there's other mechanisms for other, everybody's got a mousetrap. Their mousetrap works a little bit differently. So over in the UK, they said, you know what, we want to do a deep dive into geosynthetics and see if the tensile strength of the tensile element, the tensile strength of the geosynthetic has any direct correlation to the performance. So in other words, is that going to affect my rut depth, the tensile strength of the element? So they looked at geotextiles, they looked at polyester, they looked at polypropylene, they looked at HDPE, and what they discovered is that there's really no correlation between the tensile strength and the performance of the geosynthetic. Now, that's not always 100% of the case. There's some nuance to that. So I don't want the takeaway to be to say that tensile strength never matters. It does. But there's a huge caveat to that, in that different geosynthetics are going to perform differently. And due to years and years of research, we understand that geogrid, there's no correlation between how a geogrid performs and its tensile strength. So much so that the main two design methodologies that we use to define the benefit of geogrid are the AASHTO 1993 pavement design formula and the Giroux-Hahn formula. And in either one of these formulas, you will not find anywhere to input the tensile strength for the geosynthetic. It is all about empirical testing. So you have to empirically test, so that way you can understand how well your solution performs to be able to use these design methodologies that are accepted by the construction industry. So if anybody's got a calculator, we can whip one out and go through it, and I'll talk with it. And, nah, we're not going to do that. I've already put enough people to sleep, so we're not going to do that. But how do we understand how we can apply a geogrid to AASHTO 93 or to a mechanized empirical asphalt design, or how we can use it for subgrade stabilization and quantify that benefit. We can say with confidence, if you have a CBR of 2%, 6 inches of crushed aggregate and a geogrid will support 100,000 easel passes. We do a lot of testing. We spend millions of dollars testing this product, so that way our proof statements aren't just me up here flapping my gums. It's actually backed up by university and industry testing. So let's look at subgrade stabilization. And I read a lot of different geotechnical reports by a lot of different geotechnical engineers, and 95% of them say you can expect weak soils on site, have a plan on how to deal with it, and your options can include excavate and replace, chemical stabilization, or some sort of geosynthetic solution. But they really don't go into the specifics of what that design might be. And 9 times out of 10, a contractor's on site, they're being paid unit cost, and they're going to go to their old buddy, excavate and replace. Well, that works great for the contractor, but it takes time. It puts more dump trucks on the road, and it all comes out of the owner's pocketbook. And a lot of times we as engineers, we're there to protect the owner from, so the contractor's got everything he's looking for, and I'm not blaming the contractor. That's their job, is to put money in their pocket and to be as efficient as they can. A lot of times we in the engineering community are there to educate the owner, hey, you have different options besides just over excavation and replace. So this is the main toolbox that we would go to for the solutions to a soft subgrade. And we have summarized most of those within our design software called Tensar Plus. I was in Raleigh about 4 months ago. We had a design seminar where a room with about this many engineers, we sat down, had an all-day design workshop on using Tensar Plus or subgrade stabilization, things like that. But you all have your own spreadsheets or design softwares, things like that. That one you can use geogrid, or you can use the geotextile, or you can, just use traditional overX and replace. It doesn't matter. So when it comes to subgrade stabilization, we use a methodology called Giroux-Hahn. We also use another methodology called LAMS, Least Applied Mechanical Stabilization, which is another peer-reviewed way to calculate how much aggregate you would need to be able to pass a proof roll on a soft soil. So in this case, we've got a really soft subgrade, say 0.6 CBR, which if you're just a general civil, that means you're probably sinking up to your knee or your shin. So this is a really nasty swampy site. This is where the excavator gets stuck. This is the soils that you would be looking at. And if you wanted to be able to pass a proof roll on top of a 0.6 CBR material, you would need 49 inches of crushed aggregate. That's a lot. Even for the Raleigh area, which crushed aggregate is not as expensive as other areas, but just imagine you're in Savannah or Charleston or Wilmington. That'll buy you a new house or a couple of new houses. If we go to biaxial class 2, the good geogrid, you can do it and reduce it down to 35 inches. So I say 14 inches of aggregate with like $1.50 per square yard material. So a BX class 2, that's about $1.50. TX 160, that's probably about a $2.50 to $3 a square yard. We just saved 4 more additional inches. But if we use the best, the most expensive geogrid, the one that's going to cost about $5.50 a square yard, we can save 24 inches overall, and we can save 6 inches versus the TX 160. So a lot of times a contractor will go, okay, I'll use the geogrid, but I'm going to buy the cheapest thing possible. And that's great, but that may be the cheapest geogrid, but that's not the cheapest solution. The cheapest overall is the highest performing geogrid, which saves the most aggregate.
Yes, sir. Layers though of geogrid are there? Just one, or
typically, most cases, just one. When we start to get to load transfer platforms, or we're designing for differential settlements, not necessarily for bearing capacity improvement, but for maybe differential settlements, we may do two or three layers, just depending on what that application is. One of the applications that we have on Tensar Plus is a construction platform, which is mainly for designing cranes. So if you got a crane that's got an extremely large pick and some soft subgrades that you're worried about, you can design a crane pad on Tensar Plus, and oftentimes you might get a 5 or 6 layer solution with one of those, depending on how big the crane is, how heavy the pick. So let's look at this one more time. As the soil gets a little bit more firm, a 1.2% CBR, which means you're probably sinking maybe an inch on your boot. I sound a Canadian boot. I'm gonna stick an inch on your boot. You would need 35 inches of stone to pass a proof roll. So right on top of the subgrade, chances are you probably put a geotextile down for separation, and then 35 inches of stone. If we use biaxial class 2 geogrid that I passed around, 22 inches, we save 13. But if we use an interax geogrid, we can save Mississippi Math 24 inches total, which is the least expensive option because we reduce the amount of that aggregate down. And same thing, as the subgrade continues to become more firm, we still had it. Now there's a point of diminishing return, maybe get to 3% CBR. Okay, we can use a less expensive geogrid because there's only so thin we can make that wearing course at the top. These are just happen to be really soft soils. 2% CBR means a F-150 is probably leaving a 1 to 2 inch rut as it drives across. You get to 3% CBR, that's probably not going to pass proof roll, but you could use a less expensive geogrid than at that point. So let's look at a couple of case studies. This one is down in Savannah, but if anybody's done work in Eastern North Carolina, you're going to run across job sites just like this. CSX had to build an access road parallel to one of their rail lines to get out to a bridge to perform maintenance. The road had to be temporary, so they weren't really worried about settlement because it could settle a foot or two. Who cares? It's just a construction platform to get out there temporarily. They looked at a bunch of different solutions. One engineering firm actually suggested piling, putting in mats or putting in piling, a load transfer platform. It was hideous. And then it was going to take upwards of 60 inches of sand to be able to bridge across some of that marine sediment that was out there. So we came in with the solution using a triaxial geogrid, 2 layers in this particular instance. And I believe it was like 30 inches. So we shaved it in half over the just non-stabilized, non-geogrid solution. And then that way they were able to push out directly on the marsh grass. You can see them pushing out directly on top of that grass. Bring the sand out, clean, well-graded, not beach sand, well-graded sand out to the job site, and then pull it all back out after they were done. So there's a picture of the dozer. Obviously, you want to back dump. I don't think anybody wants to put a dump truck out there on that. This is one of my personal favorites. So this is the sunk excavator, but I got number of pictures of that. This was a project in Nebraska, western Nebraska to be exact, where they ran into this situation. And you're probably not very familiar with western Nebraska, but there's no aggregate to be had out there. It's all sand. If you're going to bring in aggregate, it's going to come in from South Dakota, or they're going to have to barge it up to Missouri from St. Louis or somewhere like that, and then rail it out there. It's extremely expensive. And the only way that they were going to be able to bridge across this was a 42-inch layer of very expensive granular fill. That is insane that they were even considering that out there in that area. So we were able to develop a solution using 35 inches and a single layer of geogrid of sand. So everybody might be thinking, well, those apertures on that geogrid, I saw how big they are. There's no way that can work with sand. We work with well-graded sand all the time. You still get the same benefit of the geogrid, that lateral restraint, using a sandy material. Now, it doesn't work well with poorly graded sand. So if it's a beach sand, but you're never going to get beach sand to compact anyway. So 35 inches of material on top of this swampy layer. They rolled the geogrid out, began back dumping and pushing, and we saved that contractor we saved the Nebraska Department of Roads, it's not the DOT, Department of Roads, several $1 million. So I love this video because this does a good job of showing you exactly how soft this material was. As this guy right here, he's about to step off the geogrid. So that's probably a CBR of about 0.5. So just having the geogrid there and that second mechanism that I talked about, the bearing capacity improvement. So basically the geometry of the geogrid itself is helping to support the weight of those workers out there. So he's just walking across it, whereas before he would be sinking up to his knee with every step. All right, so that's subgrade stabilization. Pavement optimization is another one of our large applications. This one's a little bit more in depth because we do have AASHTO 93, which most DOTs are still using. Most local agencies, counties, cities for local roads, they're using the AASHTO 93 as their pavement design. And obviously we're all well versed into it, but a lot of DOTs are starting to go to ME or mechanistic empirical design, which we're dipping our toe into that as well. But you can go on to Tensar Plus, broken record, Tensar Plus again, and you can do an AASHTO 93 design without grid, and then you can optimize it with geogrid. So if some of you probably haven't even fooled with pavement design since you were back in college, really what we're looking for is allowable easels. So the number of axle passes across a roadway over its lifetime, that's what we're trying to solve for. And the way we do that is we develop a structural number, and I'll tell you about that in just a second, over how strong the subgrade is, the strength of the subgrade. Those are the main variables that are in this formula. So if we know what we want our pavement section to look like, so 4 inches of asphalt over 10 inches of granular aggregate base, we use this thing called layer coefficients, and every DOT publishes layer coefficients. And we use that to develop a structural number. So your layer coefficient times your thickness of asphalt gives you the structural number. Then you add all your structural numbers up for GAB, layer coefficient of 0.12, which gives you a structural number of 1.2 since it's 10 inches, gives you an overall structural number of 2.96. And then here we're looking for equivalent single axle load, which is an axle load of 18,000 pounds. So one easel is an 18,000 pound axle. So that means that a passenger vehicle with 2 axles has about a 0.006 easel count, whereas a loaded dump truck equals 2.4 easels. So what we're really designing for is construction traffic and 18-wheelers, because it takes a lot of these SUVs to equal one dump truck. 4,000 SUVs is one dump truck. So if we take that structural number and we dump it here into this big long equation, it's going to spit out an easel count. So 4 inches over 10 inches over a subgrade of 5,000 PSI resilient modulus, which means about a 5%, 4% CBR, would give you a 107,000 easel count. So this pretty much represents being able to pass proof roll. You go out to a site, the contractor proof rolls the site, which means they don't leave much rut. And then that's probably a subgrade modulus, about 5,000 PSI. That gives us 107,000 easels. All right, everybody understand that? That was a lot real quickly, a lot of Greek symbols. However, if we take a geogrid, what we can do is take advantage of this geogrid, stiffening this GAB layer, giving it a higher layer coefficient, which means a higher structural number, a higher overall structural number, which means a lot more easels. So by just adding a geogrid into the pavement section, we increase the easel count from a little over 100,000 to over 500,000. So what does that look like for the owner and us as designers? So here's the original section, 4 over 10. If we simply add a geogrid into there, say, budget's not a consideration, we can increase that easel count by over 500,000. If we say, you know what, I want to save as much money as possible, let's reduce the amount of asphalt, reduce the amount of GAB, and use a geogrid, but give me approximately the same easel count, 121 versus 107, we can do that as well. And this gives you your lowest initial cost. We saved almost $7 a square yard between the original design and the optimized design using geogrid. Or it's like, I have the budget, let's make this pavement as durable as possible using geogrid. So we basically matched the cost, the unstabilized and the geogrid design, and we were able to get 356,000 easels. So there's a lot of different ways to, I hate to say it, there's a lot of different ways to skin a cat. Save money, lowest life cycle, the lowest life cycle cost, or you know what, let's make this as durable as we can with the budget that we have. And with going onto our software, if you ever use it, it's just super simple to change those section thicknesses. But how are we able, at the very beginning, I said, well, tensile strength or index properties really don't play into AASHTO 93. How are we able to justify that layer coefficient improvement, that improved layer coefficient? was a lot of testing. You know, going back to those really smart guys at Erdick and Vicksburg, we spend years testing pavement sections with them in an apparatus called the Full Scale Accelerated Pavement Tester, where we build pavement sections. Everything is laboratory controlled. We know what the CBR of the subgrade is. We know what the CBR of the GAB is. We know how thick the pavement section is. We know what the loads of the wheel loads are going to be. We know what the temperature is. They control the temperature. We know the humidity because they control the humidity. And that thing just traffics back and forth day and night for months at a time. And then at the end, to get to a few 100,000 passes, they turn it off and they measure the rut depth. So what we discovered is using that full scale trafficker, and they had 3 different sections in that trafficker, the control section, one with TX5, one with TX8, just 2 different triaxial geogrids. We were able to use less asphalt, less GAB, and we got 5 times more easels by using this geogrid section here than we did for the unstabilized. So we take that, we crunch it down, we send it out to a third-party agency to develop those layer coefficients for us. So it's not Tensar doing it, so it's an actual third-party agency, ARA, if you're familiar with them. And then they give it back to us and say, okay, these are your enhanced layer coefficients for these types of geogrids. So, all right, that's laboratory testing. That's what Federal Highways requires us to do. So now we know proof of concept, okay, it actually works. We've lab tested it, so now we can quantify it using industry methodology. So now this is a project out in Arizona back in 2015. We were able to take an apparatus called accelerated plate load testing, where it's a dynamic plate load test instead of a static plate load test. And they can actually mimic traffic loads using a plate load. It's really hard to see here. That plate load is on a hydraulic ram, and that ram will just sit there and cyclically load the ground like it's mimicking a traffic load. And what we discovered here is when we did the original design, we used a 0.22 layer coefficient for the geogrid stabilized section, and we ended up with the verified 0.31 layer coefficient that was measured in the field. So we underestimated the layer coefficient in our design purposely, conservatively, and then we were given a 0.31 that was actually physically measured in the field. So we have done hundreds of this type of test around the country. So we've done the laboratory testing, but we've also done validation, in situ verification. So it's not just laboratory testing that we did one time in a controlled manner. This is actually done in the field where you don't have control of the temperature or humidity or any of those other factors. So all that to say is you can have confidence when you're using at least our design software for pavement optimization and subgrade stabilization, because we do a lot of this with subgrade stabilization as well in the field. So here's kind of what some of that output, that's a better picture of the plate load as they're testing it here, and then they're measuring deflection at different distances off of that plate as it cyclically just pounds into the ground. All right, so there's kind of a picture of what Tensar Plus looks like. And this thing, guys, I mean, it's been game changing for us. It's so intuitive, it's so easy to use. If you ever need training on it, don't hesitate to reach out to me. I've got a bunch of business cards right here. Happy to come into your office, do a training session on it, talk about it. Even if it's just the pass a proof roll module, you got contractors that are struggling to pass a proof roll, whichever one of these modules you want to go over. So not only do we have road applications, but we also have platform. We do have foundations, which is now on there as well. So you can do shallow foundation design using geogrid. A little marine application in there. That was my baby previously. And for some reason, we have a GeoPeer calculator in there. I don't know what that's all about. But anyway, you've got a whole suite. We're constantly updating this. We're constantly validating these solutions in the field and tweaking this as well. So if you go in there today and you go in there 6 months from now, there may be a completely new module that's been added in there. Platform is a really cool one because that's where you can go in and do the crane pick designs, crane pad designs. So with that, I'm kind of done. If anybody's got questions, I'm more than happy to answer. And then I got the QR code. If you didn't get that at the beginning, you can snap a picture of that again and get your PDH automatically emailed to you.